Hi, everyone. Welcome to this panel. So I'm really happy to present our two additional panelists, and then we'll go into a discussion. We have Professor Elsa Olivetti speaking first, and her research focuses on improving the environmental and economic sustainability of materials in the context of rapidly expanding global demand. She works on two major problems: improving the sustainability of materials through increased use of recycled and renewable materials, and also material design and intelligent waste removal. And she also, the second area that she works on is understanding the implications of substitution, dematerialization, and waste mining on materials markets. Her education, she is a graduate of MIT. She got her PhD here in material science and engineering, and that's her current department is material science and engineering. She's also involved with us here at IDSS, and she did her bachelor's in engineering science at the University of Virginia. And then our second panelist is Minghao Q, and he's a postdoctoral fellow at Stanford in planetary health in the Department of Earth System Science and the Center for Innovation and Global Health. And he did his PhD here at IDSS. He was a student of Professor Noel Salin, who's the director of the Technology and Policy Program. And his research interest is at the intersection of air pollution and climate change, and he also looks at energy transitions. He is interested in sort of developing and using methods involving causal inference, machine learning, atmospheric chemistry modeling, remote sensing, among others. And so I think he's a really great example of the kinds of students that we train here in our program. He has worked on problems in China, the US, and Europe. And it'll be really great to hear a research update from him as well. So I'm looking forward to this panel. We will bring Ali into the discussion at the end. This panel is all about climate change, sustainability, and data science, and looking at these issues through the IDSS lens. So we'll transition into a general discussion of that, some of the challenges, what's going well, what's not going well, some of the opportunities that we see coming down the pike. So let's transition to Elsa. Elsa, please go ahead.
Thanks, Jessica. I think I'm mic'd, so I don't need to stay pinned. Oh, there you go. Now I'm mic'd. I have a loud voice and I talk too fast, so it's always good when we mic me. And I like to move around. So thank you so much, Jessica. It's an awesome opportunity to be here, and I'm really looking forward to the discussion. I think all of the challenges you all have been talking about the past couple of days are these rich IDSS challenges, otherwise you wouldn't be talking about them. But my very unbiased perspective is that sustainability is uniquely IDSS because of the data that exists at these multiple scales. And that's also why it's my great opportunity to be in a material science and engineering department at MIT, but also work with folks at IDSS, because I can think about things at an atomistic level, but then all the way up to how we design carbon markets, right? And so that's why, that is the luxury I have and the opportunity I have in being here. So I'm going to try very hard to just give you talk just for a little bit and give you a couple of examples of the richness of problems that we get to look at in my group, just to give you a flavor. But I also just want to give you a couple of examples of why I think it's such a meaty challenge to think about sustainability in this context. And the long list of authors I have here are my glorious students, some of whom have graduated, who've contributed to this work, and these two little stories that I'll tell you first. And I'm remiss not to mention that I bring kind of two hats in the ways I think about climate sustainability challenges. One is my research and the sort of grounding that materials that we design exist in a context, right? We don't buy the carbon nanotubes for the carbon nanotubes. It's the service they provide. And so that sort of thinking around a life cycle in the context of systems, that's sort of my research hat. But I also have the pleasure of co-directing the Climate and Sustainability Consortium on campus right now. which is a sort of industry-centric lens on what Ali talked about in terms of the climate grand challenges at MIT. And the opportunity that this is systems at another scale. We think about the company members that we have that are listed on this slide are some slice of the global economy. And so if they start to try to solve climate and sustainability problems together, maybe that's something like what a transition looks like. And so I won't talk about that so much today, but a lot of the ways in which I think about data and sustainability challenges right now is through that lens. So I wanted to mention. So just a couple of ways I think about climate sustainability, or the opportunity that data provides in terms of understanding climate sustainability. So when we think about global impact, and there's many versions of this charts that slice emissions in various related ways. This is the material-centric version of this slice, so obviously my favorite. So we think about global energy-related emissions without agriculture. We've got use of vehicles, use of buildings, and then breaking down materials contributions. And we know that metals, cement, and chemicals are the most significant part of that pie. And so what we've done, just as a way of kind of introducing the examples I'm going to share with you all, is taken the kind of roadmaps and materials-centered strategies for reducing emissions associated with each of those, but I'm just highlighting metals and chemicals here, and tried to kind of prioritize them based on their emissions mitigation potential, based on inputs, transformations, and outputs to the materials processes, and then tried to rank the red, green, yellow as technology readiness, and I've got stuff on goals there, et cetera, et cetera. But mostly what I wanted to do is, if we think about metals and cement, we've got these two dominant strategies here on the bottom that are a pretty significant part of this pie. That's about increasing recycling in a metals context, so I'm going to give you a data-driven example there, and about increasing use of alternative feedstocks in cements. So use of alternative binders in cements is another important opportunity. And richness there. I'm going to skip a little bit here. So there are many other ways in which I like to think about data and sustainability challenges in recycling contexts, in critical materials contexts, but I'm going to go over that just so I can dig into these examples here. But just to kind of reinforce, or I don't know, put a framing terminology around what I mean when I'm talking about things at an atomistic level and also a systems level, is this lens of materials industrial ecology. So folks are familiar with industrial ecology. It's this framing that, can we use strategies such as substitution, waste mining, and dematerialization, materials efficiency, using the lens of industry, ecosystems to help us address performance, but with lower impact. So that's one kind of systems framing on this. And the boundary object, for those of you who use that term in management, of choice for that community is the Sankey diagram, right? Physical flows and where they all go and where a loss is going to be. So that's the industrial ecology lens, versus or coupled with a material science lens where we're studying the control, design, and use of solid matter, and how do the ways in which we line up atoms influence the processing and the properties in the context of those. And here I've got just a schematic of steel-making processes. And those come together in the way that I like to frame the work we're doing is in materials industrial ecology. So in informing scalable design of materials by combining what our underlying physiochemical processes are with the systems context. And an example that's from material science that Antoine Allenor and Don Sadoway in my department have pioneered is lower carbon steels by through electrolysis processes, and I just use this kind of rough schematic to illustrate the sort of significant contributions that have to happen at each of these scales in order to realize lower CO2 steel as an example. So we need to think about the design of the electrolyte, and that's going to be at the molecular level. We need to think about the design of certain electrodes if we're running electrolytic processes, and that's about interfaces in microstructure in metals. We need to think about reactor design if we're going to try to scale it, but then we also need to think about, how are we building the markets, for this new product? Is it an incumbent technology, et cetera? So being able to think deeply across all those at the same time, that is the challenge we have to overcome in any of these transitions, and why it's really fun to do so, with an IDSS lens driven by the sort of opportunities for data. Okay. So now I'm going to talk about two examples. I suppose this is a thing that goes, yes, brilliant. Okay. Then I'm coming over here. so I'm going to go through two examples quickly, as I said, one in metals recycling. And the kind of details of the case I'm going to try not to dwell too much in, because what I would like to try to drive home is the role for these kind of analytics and use of data at each of these scales. So my motivating question here has to do with recycling of aluminum, because we don't tend to be able to produce supply of recycled aluminum in a way we would want to put it into the way in which it would be demanded. So there's this sort of mismatch in what we're able to collect and how we're trying to use it. And so what that makes folks think is that there's going to be this global scrap surplus, which basically means scrap we can't use because it's too expensive to get it into a way we can use it. And so based on global trends of interest in transportation in particular, our concern is around that as we electrify vehicles, we're not using as much cast aluminum, the sort of higher tolerant aluminum, but we are because we're having electrification, and we have to couple that with lightweighting that needs more of the higher purity aluminum. So this is going to maybe exacerbate this surplus. And folks have estimated, put numbers around what that surplus would be based on the lifetime of these vehicles, what the sort of global trends are. And what this looks like for material scientists is here's a set of elements I'm trying to manage in the aluminum that I'm making, and this is a set of alloy series. I'm going to make you all material scientists before I'm finished with you. It's sort of the sets of alloy series that we're looking at, and where our limits for recycled content would be now, and how that would become exacerbated over time. So it's the presence of these elements that we can't get out cost effectively that lead to our inability to use more recycled material, and therefore lead to this supply-demand mismatch. So we can quantify that as we go. So that's the sort of trend we're trying to manage. But the challenge in using recycled materials in processing, and the way we think about this problem, is this range of uncertainty, and then that just exudes data that we might look into and think about. If I'm at a plant floor trying to make an alloy of aluminum with a set of scraps, I have to manage the uncertainty both in the quality of that scrap, sort of the composition of it, but also how much. Who am I going to get it from? Where are my contracts set up? And I also have some uncertainty in the demand, and this could be as a function of time, et cetera, et cetera. So that you can already see the set of optimization tools that might be useful here, management of uncertainty tools that might be useful here. And so we've often used data-driven strategies to think about robust use of aluminum scrap at many levels, and I can talk about it. The example I'm going to mention that I'm really excited about is designing new alloys. And here, what we've been able to do, and why I think this is the two examples I've chosen are these very uniquely IDSS kinds of problems, is we're able to marry kind of different sets of data, both data that we've extracted, different kinds of data on the composition of this aluminum, on the properties we're trying to get out from this aluminum, the processing conditions. So that's kind of the data that come in here from literature, also from industry. And so there's a whole data exercise here. And then we're also trying to do an optimization of that, where I'm trying to optimize the amount of recycled content that I'm getting in that alloy. So I've got a set of data that I've analyzed, extracted automatically from the literature, which is sort of no longer exciting because of large language models, feeding it into a set of models that I'm doing optimization on, to try to predict what alloys should designers be making based on the kinds of global trends that I talked about. And so we can link a material flow assessment on one end. That's what's written up here, is that I have, not only am I able to think about the sort of composition of past alloys, but what might I project alloys to be in the future? And I can subject that to, let's skip that guy. I'm just going to show you a little mini result before I frame the last example. And so here I'm just showing you one snapshot of that model that we built. So we're taking data from the literature. We're doing an optimization on that data subject to sets of scenarios that we might envision in terms of paths forward for use of aluminum. So I can combine, here's a baseline case where I introduce a new alloy in China, and the metric of interest is how much scrap I'm able to increase. And then I might think about this in terms of increased EV adoption, increased lightweighting, and then changes in price. And so if you guys remember, the scrap surplus I told you about was on the order of 4,000. So just in this kind of simple, simple in that it's streamlined, focused example, I'm able to already start to think about how I'm changing the alloy composition as a function of these scenarios, to drive increased scrap consumption. And this is sort of data at both the compositional level as well as the systems level. I've lost track of the timer, but I think I maybe should stop there, or do I have time for my last example? Okay. So that was my aluminum story. If you remember back in my chart of materials impact, the other story I wanted to tell you was about alternative binder materials in cements. And so, we all talk about cement being cement and its use in concrete being a big environmental challenge we have to solve. It's important that we remember that's per kilogram, and it's just that we use a whole lot of it, right? So when we think about, material substitution, we have to remember, that there's two numbers there. It's quantity as well as intensity. So I like to stand up for cement when I can. But we certainly need to be addressing the footprint because of the massive quantities that we're using. And many constituents have been proposed to be used as supplements in cement. There's our friend Portland cement. We could use natural materials, natural pozzolans, calcined clays. We also often hear about the use of coal fly ash as substitutes in these materials, granulated blast furnace slag, glass, goes on and on. The opportunities might list. These are not inherently sustainable, right? I need to think about how much am I driving them around? How much am I needing to grind them and pre-treat them in order for them to actually offer benefit? And because it's waste we're talking about, it's very contextual. I can't, or natural materials. Ideally, I can design the mix, at the place I'm using the material, because then I know I'm not trucking it around all over the place. And I'm using the set of optimized materials for that particular context and for a particular demand. So it sounds a lot like my aluminum question. And so ideally, if I can inform the environmental impact, at a local context, then that offers opportunity to scale it. Because that's a challenge with use of these, waste materials is I'm going to have a little bit available here, a little bit available there. So when I think about the volumes that are important to be impacting in terms of cement and concrete, how is it possible that I could scale this as a strategy? And here's a bit of data to kind of represent that idea. Here's Portland cement in terms of the quantities that we use per year. And then here are some other those examples I showed on the previous slide of how much is available. So that definitely pales in comparison. And of that, how much is used as compared to calcined clay. Just again as a juxtaposition. So lots of different availabilities. It doesn't mean I shouldn't make use of the fly ash where it's available or the slag of where it's available. And the work that we've been particularly interested in the group, and I'll just kind of frame the analysis for, is the use of these higher volumes but lower utilization materials. So the materials I've talked to you about in my little piles on the previous slide are coal fly ash. These are produced in high volumes and very well utilized. We're very interested in agricultural residues that have a similar volume but are not well utilized. And again, it has to be contextual because it's going to vary. My agricultural residue is not a thing I know the composition of. I need to be able to figure that out. And so here's been this other awesome opportunity to leverage kind of data science coupled to material flow models, coupled to the work that we've done to extract data from the literature. So here's my final cement that I want to be pouring. And in order to make a local decision, I need to know what's the reactivity, what sorts of products am I going to form, how durable are those products going to be. And so we want as much as we can predictive models of what these alternative binders, cement is the glue in concrete, so what alternative binders might there be, and how maybe should that be mixed in a concrete mixture to produce the cement we want. And here we've had data extracted from the literature again, also lots of industry input to try to do this in a predictive way, coupled to a life cycle assessment. As I told you, it's not inherently sustainable, so I need to be able to think about that as real time as possible. So I think I'll just kind of give you a little bit of a sense of the sorts of ways in which we use this information, which is really fun. This is a phase diagram, which I need to show you as a material scientist, where I'm thinking about calcium, aluminum, and silicon, and here's Portland cement over here on the corner. But if I can think about how these, and I'm showing a couple of different wastes in different colors here, if I can think about how I might mix and match these and make local blends, then I can tell you something about the reactivity of that. I might be able to understand then doing a predictive generative model towards a cement mix or a concrete mix, which of these constituents, so here I'm just showing you the sets of things I would mix in the cement on the y-axis here as a function of how predictive is that of 28-day strength. And then I can point to, which of my supplemental cementitious materials are driving that impact, and in what way. So I think I'm going to end with this kind of overly busy, but kind of drives the point home of the work that we've been able to do in cement that again is very grounded in this data working at multiple levels way, is combining the idea of some experimental data where we can get a sense of what the reactivity of these different species are, how might they behave in kind of an industry-based flow system, but then also link that to this data that we've extracted from literature, as I told you, and thermodynamic modeling to do these sorts of designs. So if this is not an IDSS problem, and then I don't know what is. But anyway, hopefully I've given you a little bit of a sense of the ways in which I think that in order to make the nuanced, complex decisions that are the ones we need to be making in climate and sustainability, that the ability to kind of leverage data at these multiple scales and have them talk to each other and also look in kind of future-facing scenarios, we need to do lots more of. And I'll join Ali's program in order to do that, I suppose. And I'll leave you with this Sankey diagram. I'll leave you with this sort of image that I use a lot in the consortium. When I think about how we need to transition the economy, we need everybody there at all times. And so this idea of like what are ways to have the system in the room to think across the sorts of transitions that we need to do in the biofuel space and leveraging materials to decarbonize the grid. And so this is a Sankey diagram of emissions in gray. And what I've done is sort of overlaid the members of the consortium that I showed you at the beginning, the sort of different companies we have represented and who we're working with. And the black dots are the companies. The colored dots are actually the MIT community and how they would kind of work together to help with some of these transitions. So this is why we need IDSS. Thank you for listening.
All right. Good morning, everyone. Thank you so much, Jessika, for the nice introduction. So as Jessika said, I am IDSS product. I graduated from the Social and Engineering System program in 2021. And when I got the invitation, of course, I'm really excited. And I think about the memory I had as a first-year student attending the launching ceremony. And so you can't imagine, like, things, IDSS and my own trajectory has come such a long way. So I'm really excited to be here, very special to be here for myself, talk to you a little more about my thoughts, integrate statistical and physical modeling to understanding causal effects of climate change and policies. So, and I think this is nicely connected to sort of the big picture Ali set up earlier, and also a lot of the discussion we had in the yesterday session. So we care about causal understanding, we care about how climate influences humans and how can we design policy and solutions to address those problems, right? So some problems like what would happen to the wildfire risk in California if we increase the ambient temperature by, say, 1 degree, or from the policy side, what would happen to air quality and children asthma rates if we replace coal power plants with renewable energy generation facilities. So from the methodological point of view, so broadly speaking, we have two sets of methods that we can tackle this causal question. So one is the empirical data-driven approach, and the other would be physical modeling approaches in the climate environmental domain. Right, so the yesterday session covered quite a lot on the empirical statistical approaches. So they are driven by empirical data, and there are a lot of ways to frame that, but often they're framed as randomized experiments, or often in this situation, we are not allowed or cannot do experiments, so it's often based on observational data, so they are natural experiments. Right, things like we are interested in how a heating program influences the air quality. So we have air quality measurements, and we try to understand how it changes before and after a start of a program, for instance. On the other hand, especially as atmospheric scientists, climate scientists, we have strong tools that are process-based modeling approaches, and they're driven by complex physical, chemical, biological, ecological processes, and some models are simple, some models are really complex. They are run at the supercomputers. And we can also derive causal insights from those methods, right? We run so-called model experiments. We run a lot of scenarios, and across the scenario, we change some parameters and fix, all the other components fix. So the changes in the outcome are attributable to that parameter we changed. So we also have causal interpretation that way. Right, so example of that would be the complex climate system models, which sort of really form our basis of understanding of climate change and how it influences humans. And as you may sort of imagine, that those two group of people don't really talk to each other. So there is this discipline barrier that the empirical methods are largely used by data scientists or social scientists, economists, political scientists, while on the other hand, the modeling approaches are used quite a lot by natural scientists, such as atmospheric scientists and climate scientists. And what I'm going to argue right now with some of my own work, and I think this is really made possible by this unique IDSS, the unique mission of IDSS is the integration of the methods will lead to better science and larger impacts. And please also bear with my choices of the MIMS, and that's based on my very limited understanding of the MIMS. Okay. So I'm going to address those or demonstrate those integration in the discipline or in the topics I personally work with. So that's at the intersection of climate change and air quality. We already know that compared to pre-industrial times, our temperature has increased by 1.1 degrees C, and it has led to all kinds of problems that we're seeing right now. And on the other hand, we know air quality is bad for human health and is the #4 killing factor across the world, killing more than 7 million people every year. So broadly speaking, there are three ways that I think of this integration between empirical data methods and the modeling methods. So one is the simple ways to comparison. So we use the two methods to analyze the same problem, and we try to understand, do they give you the similar conclusion? If they're different, why are they different? There is also the complement approach. So each method has a set of questions that is sort of better answering at. And since the question we try to answer are super complex, we need all of them. So we use one method in one part of the problem and the other in the other part of the problem. So we get the full picture. And also, I think the more interesting one, but also the really challenging one, would be the dialogue. So there are not just one way interaction, but multiple ways of interactions. So there are also a lot of ways that those methods can dialogue or talk to each other. So I'm going to talk a specific form of dialogue. So that's using one method structure to inform the decision of how we do the other method. Okay, so this will be drawn. So for today's time, I'm just going to focus on give you two examples, one on the complementary idea and one on the dialogue idea. And this will be drawn by a lot of my own research with a brilliant group of collaborators, including people at MIT, Stanford, and other places. So for this complementary idea, so I'm going to talk about this using the work that we're trying to look at how does wind power development influence air pollution and this related environmental justice, right? So decades of work have shown that people are not exposed to pollution in the same way, right? So in the US, racial minority groups and low-income people, they're exposed to higher level of pollution. And then the question is, how can we address them, right? What do we do about it? So our work is trying to understand how we'll development of renewable energy, wind power specifically here, how would it influence air quality and the disparities. And this is also very policy relevant. At the Biden administration, ordered that 40% of the benefits from all federal climate and energy actions need to go to the disadvantaged communities. So here is an example that I think that, this is an example that we combine the statistical causal inference with chemical transport model, the atmospheric models. So this is a complement approach that we think really by integrating the methods, we get the full picture, right? So here is the causal chain. So we have development of wind energy, and the wind energy can replace electricity generation from coal or natural gas power plants. So we have then, it could influence the emissions from all those fossil fuel power plants. And those emissions can react in the atmosphere in a very complex way, and they can transport long range, and it forms the air quality. It changes air quality and has different health implications. Okay. So in the first part, because we have really good data sets, we have hourly wind power data and hourly SO2 and NOx emission. Those are the two pollutant precursors from those coal and natural gas power plants. So we have very good data sets, so this is a good setting for doing this empirical evaluation, and this also has causal interpretation because this is somewhat a natural experiment as the wind power really fluctuates in a quasi-random way. And then for the second part, we're going to leverage the ability of chemical transport models. These are, again, the models that run on clusters that have the ability to simulate the concentration of all kinds of chemical species in the atmosphere. And specifically, we're focusing on the PM2.5, the really small particles, and the ozone here, which are shown to have a lot of negative consequences on human health. And then so we can simulate the changes in PM2.5 due to wind power differences, and then we can link this to where people live and think about the distributional implications. Okay. So at the high level, I'm just going to have this two slides of the results. So here what we see is by combining these two approaches, that development of wind power does improve air quality and reduce premature mortality due to the exposure to air pollution. So here specifically, we're looking at the percentage of the air quality benefits that goes into either the low-income group or the minority groups, right? So this little dot here shows that so about 30% of the benefits goes into each group, and this is below the 40% administration target and sort of below or at the level if these benefits are just evenly distributed. One really interesting thing we find in this work, so if we sort of tweak the energy system a little bit, so with the same amount of wind power, if we let the wind power to replace a different set of fossil fuel power plants, so we can end up having larger overall benefits, so we can reduce more emissions and improve more air quality. But surprisingly, this still consistently, this only about 30% of the benefits goes into each of the disadvantaged communities, and this is still falls short of the disparity outcomes. And this is a result of the locations of those coal and natural gas power plants and the range of this pollution transport. It sort of ends up benefit everybody, but really doesn't do much to reduce the disparity between different groups. Okay, so pivot a little bit to talking about the second example. So this is on the dialogue idea. So, and I'm going to illustrate this with a project. So how we think about correct for weather variability in policy impact analysis. So a lot of the empirical work trying to understand if we adopt some kind of emission policy change, so if it's a heating reform or it's adopting more EV, how does that influence air quality? And we have the real world data. So one challenge to do this empirical work is we don't really know is about the weather variability, right? So before and after the policy change, the weather changes, and weather is an important factor in determining air quality. So people know this is an issue and have used all kinds of tools to try to correct for it. So for instance, here is the tool by the US EPA Environmental Protection Agency, and they have their preferred model, a generalized additive model, which is just a nonlinear regression model, and they try to correct for the meteorology effects on ozone. And there's the raw data, and there is this corrected data. The question here is, so this is really a causal inference question, right? So can those tools really recover the counterfactual that we're interested in? And this is not really obvious. This is pretty hard to do in the real world, and this is the fundamental challenge of causal inference, that we don't really observe the counterfactual with data. Like we don't know how pollution looks like if the weather is not like today's weather, if it's like yesterday's weather or last year's weather. But this turns out to be a perfect setting for a combined model to answer this problem, right? So in the real world, we only gonna observe the observational data with the real weather pattern, which has all the variability and dynamics. What we try to do is to use different methods to correct for this variability and get this counterfactual under the fixed weather. But this is not able to get in the real world, so it's sort of really hard to understand the performance of this correction methods in the real world. So we turn to the model simulation, and this is something that model is really good at simulating. So we can simulate two runs of scenarios. So one is simulation with the real weather variability, and the other is the simulation with the fixed weather. And then we can use this as a proxy data, so we can apply our different kinds of our correction techniques to this simulation with the weather variability and see if it can recover this run with the fixed weather. So specifically, we're interested in the case study we're looking at is the last decade's air quality improvements in the US and China. So we have this two set of scenarios. One is what we call the observed scenario, which is under the changing emissions and changing meteorology. And the other is the counterfactual scenario, which is changing emissions plus constant meteorology. So in the counterfactual scenario, by design, there is no weather variability, so the signal is purely driven by the emission changes. And in the observed scenario, there is weather variability, so we need to correct for it. We use different kind of methods and see if the estimated trends will match the emission-driven trends. Okay, so unfortunately, you don't really see the colors at all. And it would be hard to imagine, I guess. So I will just let you to look at the numbers. So here would be the counterfactual scenario, which doesn't have the weather variability. So what we see in the counterfactual scenario is ozone is declining because of the strict emission control policies. And when we don't do any correction, so it ends up having a pretty large error. It doesn't really matter about the unit. And then when we use, say, the EPA's favorite methods, it sort of reduces the error a little bit, but really not too much. Right? It still remains pretty substantial. And then we look at some other methods, such as random forest method, and we end up having our own method, which combines machine learning with some synoptic information insights derived from atmospheric chemistry. And this one gives you sort of the better performance. This is the error term, so the lower the better. And so this is sort of lower, but still not ideal. Okay. So why are we doing this exercise? And also just to thinking back to the big picture, right? The big picture is we try to do this empirically, right? To apply this to the real observational data we have. So we then apply all those insights we learned to the real world data, so the PM 2.5 and ozone measurements. So they are measured at all those little dots. One dot is a minor across the US. Okay, the color here is good. Okay, so what we have here is, so I'm overlaying the trend in ozone concentrations in both the model world and when applied to the observations, right? So what we try to do here is we try to get the red bar for the counterfactual. So red bar is the observational data. We try to understand what's the counterfactual ozone trend in the real data. But that's, of course, not able to get because, again, due to the fundamental challenge in causal inference. But what we can get is this is to have this exercise in the modeling world. And the idea is basically in the modeling world, so that's the blue bars, one of our methods or our preferred methods have the estimate that's closest to the counterfactual simulated in the model. So perhaps the hypothesis of what we learn in the modeling exercise could also be relevant in applying to the observational data. Right? So again, thinking back to the big picture of the integration, so we try to use the model's structure to inform how we do the empirical analysis, and then we do that still with the empirical data. So that's, I guess, one not really perfect form for the dialogue. Okay, so again on the slide, so I really think that throughout my training here at IDSS and my own research, and this is also a big part of my future agenda, that I think the integration of these two methods really can lead to better science and higher impacts. And again, not bragging about IDSS, but really I think the IDSS is really a great place that really makes this integration possible. Thank you very much.
All right, so we will transition to a Q&A now, and I'd like to invite the panelists to come up here. Do we have another, okay, there's a mic there for questions from the audience. Great. I'd like to start with turning to the audience. Do we have any questions for any of the three speakers? Yes. Please go ahead.
Hello. Hey, I'm Mark from Munzer's group. Had a real quick question actually for you, our last speaker. You talked about the synoptic model in the case of predicting ozone, where you used a random forest, but you also used some atmospheric physics understanding. I think that's a really interesting point where you're bringing together machine learning and sort of that raw physical understanding. I was curious to learn more about how you guys did that.
Yeah, Absolutely. Thanks for the question. So what I would want to say is what we do is a pretty crude and crude way to do that, which I think there will be a lot of improvements. So what we do is we know for a long term of the atmospheric chemistry understanding that this locations, let's say Boston ozone today, does not only depends on Boston's weather, but also it could depend on like weather pattern 1,000 kilometers away. There are this larger scale circulation patterns. So what we do is we be lazy that just through all the features, all the locations in the United States weather in it, and sort of let the model to choose. So, so there are, say, Seattle's weather today, there are Houston's weather today, and sort of we try to let the model learn if any of those locations information will be helpful. And it turns out it can learn, it generates a performance that sort of outperforms all the other methods. I do think a more physical informed way could make better. So like we, instead of throwing all the location in it at the same time, we can do something if there is informed circulation pattern, so we can be a little more selective. But that's how we do the model currently.
Okay, so if we don't have any other questions from the audience, I'll ask a couple, and then if anybody thinks of anything, feel free to make your way to the mic here. So I have a question around data limitations. You know, in today's world, we often talk about all of the data we have. We have overwhelming amounts of data available to analyze, but when it comes to sustainability and climate change, often we don't have the data we really want or need to answer a particular question, either because the data is proprietary or because there hasn't been a sort of incentive to collect it. It's costly to collect. There's little economic value to collecting it. So I was wondering, in your areas, each of you, and Ali, I'm going to ask you this too, because I know you've been sort of digging into this area and designing your curriculum and this major. In your areas, if there's one set of data that you could ask for and be given, what would it be? Or alternatively, what are some of your, what are some of the missing data sets that you think we should really be highlighting, thinking about collecting? So, does anyone want to start?
So I'm going to speak not based on, this is far from what I do in my research, but based on discussions I've had over the past 3 years and longer with colleagues. So if there's any inaccuracies, it's my reflection of what they said, not what they said. As you know, remote sensing is now a big part of for us to sort of better understand the Earth system. And one of the key challenges we have right now is that we have now realized, although many people knew before, but were not listened to, that natural gas is not as clean as it was, advertised a decade or decade and a half ago. So we thought natural gas is the good fossil fuel that is not as bad as coal. So if we replace coal with natural gas, we're going to have a huge win, and we're going to get borrowed time, and hopefully technology will take care of things, and we get an extra 50 years or whatever. It turns out that because of methane leakage, natural gas is, by some estimates, actually worse than even coal. So I don't know if that's true or not. There's a lot of debate in the literature how true that is. But one of the key challenges is try to sort of estimate correctly the amount of methane leakage using a variety of methods. And I think this is a very hot area that combines data science, signal processing, physical modeling. And it also reflects to sort of, there's an interesting policy angle to this as well. Oil companies or fossil fuel companies do not like people, snooping around. And so there is legislation that limits, what you can actually do, because, and so figuring out non-invasive ways of actually remotely sensing, and then when you get this data, how do you integrate it? The other aspect is that we lack data on is, so there are these big climate models that give you sort of the general trends, but if you want that data to be useful for any particular location, you need local data to sort of localize the trends of that model. There's a lot of interesting algorithmic, scientific, statistical, and otherwise, information science issues there that are really exciting. And how do you aggregate these coarser global models with local models? But we don't even know what kind of data allows you to better, more accurately describe things. So these are the two things that I've heard from colleagues.
I was actually going to say that it's very similar to what Ali said. So maybe there's sort of two things. One is kind of unlocking in my own work, but I think in terms of climate sustainability, the ability to accurately measure emissions is going to be and is essential. So I think that is, and you mentioned this sort of at the local level, the ability to scale it, because there's so much that's pinned to our ability to incentivize that's based on that. So I think we could probably just say that many times on the list, and that would be, in terms of carbon pricing, in terms of everything. And so I think the ability to, in multiple different, in the air, in the ocean, in the soil, the ability to cost effectively have practitioners understand what is happening to not just carbon, everything. And so that I think is the most important data I would put at the top of the list. In terms of things like, in terms of climate, one thing we talk a lot about in the recycling space is the ways in which the materials passport sort of, so maybe the broad category for my second data set is like data across supply chains. And I get to cheat by many things are in that list, right? But the ability, the folks we work with are often talking about, things being trapped in recycling jail, which just means we can't make use of them because we don't know what they are effectively. And so, traceability in that sense also has very broad sweeping implications in local communities and, and at the mine level, and that, that's only going to become more so. So that's not really a fair answer to your question because I basically just said everything, but it's everything framed in a lens of what it could unlock.
Yeah, I think those are really great points. I just want to add in one more dimension on this is the geographical inequity in the data coverage. So especially for like the field I work with, which is air quality and climate change. So we know that, say, places like sub-Saharan Africa, they are just really the most vulnerable communities to some of the climate-induced pollution changes like wildfire or dust. And like I showed this map of the old air quality monitors in the US, and they're like 1,000 monitors, which we don't think is enough because we have a lot of areas not covered. But like in the entire Africa continent, there are like less than 10. And so, well, I'm speaking about the publicly available ones, but so I think with the introduction to remote sensing, there are people have been talking about this, have tried to fill in a lot of the data gap, but still you need really very good quality ground measurements to help validate the remote sensing and help you really as your machine learning labels to construct estimates. So I know there has been a lot of efforts trying to develop more networks there, but I definitely think that since we are talking about global climate change, that's definitely a very important area that we lack a lot of data.
Yeah, so I mean, one of the reasons I wanted to highlight that issue is that I think here at IDSS, we're doing data science, it's a very broad term, but we're also doing problem-driven research. And so I think it's a really nice place and an opportunity and really important to think about what we could do if we had the data that we wanted, what more we could do, and to then come back to that, instead of just taking all of the vast amounts of data that we have and then kind of developing our methods, irrespective of the really important societal challenges that we face. Instead, we're really focusing on those challenges, but then also trying to, be at the forefront of methodological development. So I think it's a really nice intersection, and also we have a great opportunity to highlight where data is really needed, where it could make a difference, and then share that message, which could maybe slowly bring about change and greater investment in data collection and
Jessica, can I make
so
one
forth.
quick point? Sorry, one term that captures a lot of what you just said that's been used a lot in the materials community lately is AI-ready data for the problems we need. So that sort of thinking about that, like you said, there's this sort of reams of stuff that we spend a lot of time doing. So kind of framing it in this sort of problem-driven, AI-ready way is something that the materials community has started to think about.
Yeah, I think that's great. And so if we don't have any other questions from the audience, I did have another question. I'd like to hear your responses. We're going to try to wrap up at 11:25 here. But so on the side of models, I think all of you touched on, and our curriculum touches on, this intersection of data-driven models, theory/mechanistic models, making predictions that are testable against data, and then simulations. And, I think certainly in the research presentations and also in our curriculum, we're sort of trying to wrap our heads around what is the right intersection there for particular problems of interest. And essentially being able to make, I would say, although this isn't a comfortable word for everyone, but to make better predictions about, if we take these steps, like in materials design and limiting air pollution, then we will, we can expect to see this range of outcomes. Ideally, we'd want some sort of probabilistic forecast. And so my question for you is kind of thinking about your areas of research. How do you think about that intersection of, data-driven models, theory, mechanistic models, and Minghao, you highlighted, those two approaches, I think, although I think you were lumping together the mechanistic models and the simulations, but I'm kind of separating them out for the purposes of this question. So at that intersection, let's say like taking a particular question of interest, how would you ideally combine these three methods? Kind of what is the forefront, what does the future look like in terms of research, bringing together these three approaches? What new things could we learn? Can we make better predictions is really essentially my question. So it's an easy question. Yeah. I don't know if anyone wants to go first.
I'll take a stab. So I think the question that you ask doesn't, it's sort of universal in any complex scenario. You do get these settings. We grappled with this when we were with our colleagues in IDSS sitting here. We were discussing modeling of, during the early stages of the COVID pandemic when we were thinking about trying to get predictions of the spread. So you had all these, sort of vanilla textbook models that maybe give you get the sign right, but there's so many details that you're missing that are not quite accurate. And then you have these reduced form models. And I guess it depends on what question you ask. It's hard to say. There's sort of no sort of normative way to say that, okay, this one is better than the other. It very much depends on what kind of question you want to ask. And this also, in broad areas of social sciences, this also comes up, of whether you want a structural model or when you want a reduced form model. So reduced form models, you just do a regression, linear or nonlinear one. And whereas structural models, you try to get a mechanistic, your goal is more than prediction. You try to get a mechanistic understanding of what goes on. So if you have a physics for your problem. I think again, from what I understand from colleagues who do climate science and engineering, this is really the difficulty. We understand the physics, but we can't simulate the physics. We don't have enough computation power. It's so complicated. You can't run the Navier-Stokes for the entire planet. You can pick one small tiny grid and do things in detail. And then what you can do is you can have these sort of very coarse larger models. And then the question I think a lot of people are trying to figure out is how do you transition from this very microscopic, detailed local model to these global models? How do you stitch them together in a computationally tractable way? And that's where a lot of tools of machine learning have shown some promise, although the jury is still out on how useful those things are. There's a lot of hype around them, but I don't think the community is still convinced that that there's gonna be a magic bullet there. That's my understanding.
Maybe another little angle on this that we found useful. I don't know, this is a direct, well, this sort of can we make better predictions question maybe is a little bit what this I'm trying to say here is I think a lot of the way we've been trying to use the interaction between, kind of doing simulation projections with, kind of more predictive work versus empirical work is where we put the domain expert and how and so it ends up being kind of parts of these models are to inform the domain expert of where to search or where to probe other questions. And in both of the cases I gave, it's true, but in other examples I can think of is this, we often are doing the work with industry and they're, going to then test the alloy. And so having them see where it is that this simulation put this relative to where this optimization is, and then that's kind of brute force or, sort of manual integration, but then it's about informing those who would use those models. So that's not a fancy algorithm, but it's just the way we've been trying to, kind of create that intersection.
Yeah, just I think quickly add on this. So, so I showed the 3 layers in one of my slides and talk about the sort of the more interesting, perhaps the complement and the dialogue one. But what I think is really important is actually the comparison one, because that just bring everybody into the same field. Like what you often see is like because of the different people don't really talk to each other. Actually, there are more similarity across how different fields think about one question. So I think there is probably going to be a lot more room we use a different set of questions to answer the same set of important questions and see what are something we really agree with each other and what are some of the differences. And that help us to build this conversation that between the different groups. And I think that will really help inform the sort of what's a better integration in that sense.
Yeah, that's great. Yeah, I mean, I think, Elsa, with the work you presented, you start out in a sense with a simulation that highlights important areas, and then you make a data-driven prediction in a sense, and then you're saying experts come in and then resolve the mechanisms, perhaps, right? And then Minghao, in your area, you're saying, the example you gave was, I guess, we can compare data-driven predictions and the outputs of simulations, and then where they disagree, look for the underlying mechanisms, many of which we understand in terms of the underlying physics driving climate change, but we don't necessarily, I think, understand those mechanisms at higher levels, somewhat more aggregated levels. So anyway, thank you all. This was fun, and thanks everyone for listening. We'll wrap up, and I think we have our next session coming now. So thanks so much.